In the first part of section 19, we will look at zeros of a polynomial function. The use of the calculator is not allowed. For each of the functions below, you're going to identify the degree and list the type of each. In each of the models, we want to notice that they're not in standard form. There is a little bit of multiplication that needs to be done. But in order to identify just the degree and then list the type of each, we really don't need to multiply everything. What we do need to pay attention to is the highest degree in each of the sets of parentheses, because if we were to multiply those together, what we would get in this case for model 1 would be x to the third. Therefore, the degree of that is 3, and that means that it's going to be cubic. For model 2, we'll look at the same thing. We'll take a look at the highest power in each, which is going to give me x to the first and x to the second. Then as we multiply that again, that would give me x to the third, which means the degree is 3, therefore it's cubic. So take a look at examples 3 and 4 and see if you can do the same. And in example 3, again, we have an x and an x squared multiplying together to give us x to the third, which will give us a degree of 3, and that's going to be cubic. And then in model 4, we're taking x squared and multiplying it by x squared. And when we do that, we get x to the fourth, which is going to give us a degree of 4, and we call that quartic. So do the same for examples 5 through 10. And in example 5, we notice that we're multiplying an x squared with an x squared, which is going to give us x to the fourth. Therefore, it's a degree of 4, and it's quartic. For 6, we would be multiplying 2x squared with x squared. That's going to give us 2x to the fourth. So again, that's a degree of 4, making it quartic. For number 7, we would multiply 3x with x squared. That would make it 3x to the third. Therefore, the degree is 3, which we call cubic. For number 8, we've got x times 6x squared. When I multiply those two together, I'm going to get 6x to the third. Therefore, the degree is 3, which we call cubic. For number 9, we multiply x times x squared. Again, that's going to give us a degree of 3, and that's going to be cubic. And then for 10, we would be multiplying x squared times x squared, giving us x to the fourth. That's a degree of 4, which is quartic. And what we really want to pay attention to here and know going forward is that the degree of the polynomial tells us the number of zeros in the polynomial. Now in model 1, we can see that the degree, we already talked about the fact that the degree would be 3 here. And therefore, when we're looking for our solutions here, we're looking for 3 solutions. Now, when we go to find our 3 solutions here, it would be easiest if this was already factored. The x plus 2 part is already factored for us. What we'll want to look at is this x squared minus 5x plus 6 and factor that. And as we do that, x squared minus 5x plus 6 is going to give us x minus 3 times the quantity x minus 2. So now we have these 3 factors as part of our problem. So if we set each of these factors equal to 0, x plus 2 equals 0, that's going to give us a negative 2, and that's considered a real solution. For x minus 3, if I set that equal to 0, I would add 3 to each side. That's going to give me a solution of positive 3, which is also real. And then finally, if I set x minus 2 equal to 0, that's going to give me 2, which again is real. Now for model 2, we would like to try to do the same thing. So we start by trying to factor the set of parentheses right here. But unfortunately, this time, those are not factorable. So we need to think about our other options for finding the solutions there. And what we'll want to do is use the quadratic formula. So take a minute to use the quadratic formula on x squared minus x minus 1. Now we know that if we set x plus 3 equal to 0, if I subtract 3 over, I should be getting x is equal to negative 3, and that's considered a real solution. Then if I went to do this part, we would start with the opposite of negative 1, so that's the positive 1, and you can see that in both cases. Then we put plus and minus, and here I've written them as 2 separate problems, but if you just have it as plus and minus, that's okay. The square root of b squared, so negative 1 squared is 1, minus 4 times 1 times negative 1, and that's going to become a positive 5 there, all divided by 2 times 1, giving us 2. So again, giving us these 2 answers. Now because they didn't have i's in them at all, again, that's going to be considered real for all 3 of those. Now looking at model 3, you're going to want to do the same type of thing. You're going to try to factor it. If you cannot factor that set of parentheses right here, then you're going to look at the quadratic formula. Once again, this is not factorable. So when we look at this, we want to use the quadratic formula. So we've got x plus 1 equal to 0, and that's going to give us -1, and that is definitely a real solution. Again, doesn't have an I in it. Then when I'm looking at this part right here, the opposite of -1 is +1, so I have that in both cases, plus or minus the square root of b squared. So -1 squared is going to be 1, minus 4 times 1 times +1 this time. So I end up getting 1 minus 4, which is -3. Since we can't have the square root of a negative there, we do take out the I. So we have plus and minus I root 3, and then all divided by 2 times, in this case it's 1, so we put 2 in the denominator. And those represent our 3 different solutions. Try the same thing for model 4. And we want to notice in model 4 that the first set of parentheses is actually exactly what we just worked with right here. So there's really no need for us to try to factor this or to use the quadratic formula to find those answers. So what we'll do is just go ahead and transfer these 2 answers over when we're talking about this example. We do, however, want to look at x squared plus 4 and think about our method for that. It is not going to be factorable. So what we'll do here, what would make the most sense, is to solve this one by square roots, because I've got a squared part and I've got a constant part. So here I subtract the 4, giving me x squared equals -4. Take the square root, and when we take the square root of a negative, again, an I comes out. The square root of 4 is 2, and we always put plus and minus there. So this is 2 of our answers, and then again, we talked about these are the other 2 answers. So what we have here is we have these 2 are complex answers, and then these 2 are imaginary answers. And one thing you want to note is that the complex or imaginary answers, they always come in pairs. So you'll notice that we have these 2, and we have a positive version and a negative version, and then the same thing over here. So you can't just have one complex answer without the pair of that. Okay, so try number 5. And in number 5, again, I'm going to try to factor. Here, everything was factorable. So in this case, I'm getting x plus 8 times x minus 1. And then over here, I'm getting x plus 1 times x plus 5. I know I'm expecting to get 4 answers here. So as I set each of these sets of parentheses equal to 0, I am going to get 4 separate solutions. Those solutions are going to become -8, +1, -1, and -5. And those are all real solutions. Try number 6. Again, we said that the degree was 4 here, so we're looking for 4 answers. I'm going to try to factor them. When I go to factor it, this set of parentheses right here is factorable. So I got this. However, this set of parentheses is not factorable. So I'm going to be able to set each of these equal to 0 to find those solutions. But with this, I had to use the quadratic formula, and you can see that here. It's going to become a +2 plus and minus the square root of -2 squared, which becomes a +4, minus 4 times 1 times 9. I end up getting 4 minus 36. And so I end up with a -32 on the inside here. And as I break that down, I end up being able to take out a 4, also the I, and then I would still have a 2 left right here. Now, before we can finish this problem, we do need to look at the 2, the 4, and this 2. Because all 3 of those are divisible by the same number, I can go ahead and reduce this just a little bit further, making this 1 plus or minus 2I root 2. And then going back to this part right here, if I set each of those equal to 0, in one case I'm going to get -1/2, and in the other case I'm going to get +3. These are both real solutions. These are both complex solutions, and again, we wanted to make sure that they did come in a pair there. Try number 7. And in number 7, this one is factorable. So 3x plus 1 saves 3x plus 1. This set of parentheses here gives us this. Now as I set each of those equal to 0, my solutions become -1/3, -4, and -2. And once again, those are all going to be real solutions. Then over here, Again, I have a degree of 3 here, so I'm expecting 3 different answers. X minus 7 is going to stay x minus 7. I attempt to factor this. It is not factorable though, so we are going to have to use the quadratic formula. And when we do that, that negative 1 becomes positive 1 plus or minus the square root of negative 1 squared, which is positive 1 right here. And then this is minus 4 times 6 times 1. This right here is going to be minus 24. So I have 1 minus 24, which is going to give me negative 23. And then because the 23 doesn't break down, the 23 stays inside the parenthesis, but then the negative we can take care of by taking an I out. Now in the denominator I had 2 times 6 giving me 12 here, and so to finish this I look at this number, the number in front of I here, and then the 12. If they could all divide by the same thing I would do that, but in this case they cannot. So my final part here is then setting x minus 7 equal to 0, giving me positive 7. That's of course a real solution. And then what we got here is a pair of complex solutions. Take a look at number 9 and try this one. Again, we're expecting 3 answers. Now as we factor this one, we will get x minus 5 and x minus 5 for this set of parentheses. Now, since we were able to factor everything, we can set each factor equal to 0 to solve. So this is going to give me a negative 3. And we've seen this before. We've got x minus 5 twice, so there's no need to set x minus 5 equal to 0 because we would get the same answer twice. And so we just have a 5 there. And we call that a double 0. So you can see by the note down here that a 0, which repeats twice, is referred to as a double 0, and that a 0 that repeats 3 times is referred to as a triple 0. Try number 10. Again, we're expecting 4 solutions. And when we factor this one, it is fully factorable. We get x plus 3 and x plus 3 for this set. We get x minus 2 and x minus 2 for this set. Now, as I set them each equal to 0, I end up getting, it's 2 of these. So again, I'm going to call that a double 0 at negative 3. And then again, 2 of these, and that's going to become 2, and that's again a double 0. In both cases, they are going to represent real solutions. So a few things we want to talk about with the graphs is that when we have real zeros of a polynomial function, they're going to show up as x-intercepts on the graph. So we'll actually see them crossing the x-axis. But if we have complex zeros of a polynomial function, they will not be x-intercepts of the graph. So they will not cross the x-axis. And then finally, when we see this double zeros of a polynomial function will be tangent to the x-axis. So what happens in those cases is you'll see that it touches the x-axis and then reverses directions. So please complete the exit slip that goes with this lesson and practice set 19.